We have another theorem in Young's geometry. This one says that in Young's geometry, every point is on at least 4 lines. Now, we're working our way up to prove that every point is on exactly 4 lines. The way we're going to do that is we're first going to do the less than, then we're going to at least 4 lines, then we'll do at most 4 lines. And when we have that, we'll have exactly 4 lines, excuse me. So we need to prove that each point is on at least 4 lines, and we have several cases. So if you think about, we're going to use Theorem 1 that says that there are 4 points in Young's geometry, at least 4. So if we have this arbitrary point P to start with, then there are 3 others. And if you think about it, there are a couple of different configurations that they could take on. And let me walk you through the cases and see if I can explain. Sorry. There we go. There's case 1. So case 1 says that there's only 2 lines that go through P that contain all of the 3 points. Okay. And then case 2 and 3, they're going to be 3 points, but there's a couple different ways that they can be configured. So you see here, case 2, there are 3 lines that go through these points A, B, and C, but these points are collinear, right? So we end up with a situation where the 3 arbitrary points that we've chosen happen to all be on the same line, all right? And so then the last one, sorry, trying to click this, is case 3. Now we have 3 points, but they're not all collinear, right? So instead of the point being here and being collinear, now we have 3 points that are not collinear. And I want to make it clear that I'm not proving this based on the model. I drew it out so you could see different pieces and aspects of the model, but we can test it on other points, and I'll do that in a minute. Okay, so let's go through case 1. All right, sorry, case 1. Okay, so the 3 lines, the 3 points that are added happen to fit on 2 lines. So we're just naming them. We can do this, right? They're arbitrary, and we're saying, hey, whichever line has 2 points on it, call it M, and label the points that are on that line A and B, right? So it doesn't really matter. I don't really name them up here, but you could name them A and B. But we're allowed to do this. There are points there. I can call them whatever I want. There's a line that goes through 2 points. I'm calling it M. It could have been down here. If there were 2 points down here, then we'd name this one M. And we have a second line called N, and we're saying, hey, the point that's on it is C. Okay, that's fine. That's just the givens, right? There's nothing really to justify there except to show that these are the only configurations, these cases are the only configurations possible. So now we're going to construct a couple of things. We're going to construct the line CA and CB, right? So we're going to connect the point C to the other 2 points, A and B, right? And why are we doing that? Well, the point is that, or the point, yeah, they cannot intersect. Why is that true? Well, if they had an intersection point, say this was an intersection point, now there would be this line that connects C and this intersection point plus this one, right? So we would have 2 lines that connect the same 2 points, and that would be a conflict with the axiom that says every line is on, every pair of points is connected by a unique line. So let me get rid of these lines. They can't intersect. So now, if they can't intersect, they both have other points on them, right? So when we put those points in, here's the point that was on this line, and here's the point that was on this line. Well, there have to be lines connecting them. Okay, well, why couldn't a single line from A connect them both? Or from the point P, sorry, connect them both? Well, again, we have the same issue, right? Let me change colors here. Right, I would have one line connecting them. I'd have this second line connecting them. Then I have, right, this one goes up here and this one goes here. So I would have these two yellow lines that both were on this point P and this point here, right? So when I construct these two lines, they can't overlap. So let me switch back to red. I like that best. And get rid of that. So that completes the first case, right? That we start with the two lines that contain the points. We create lines from the point that was just on, that wasn't collinear with the other three, to the points that aren't P. And they can't, those two lines can't intersect, so there are 2 points on them. And then that gives us lines 3 and 4, right? So we had lines 1 and 2 here. Do the construction, create the points, draw the lines, and then this line, the orange line that we added in and the diagonal, are now, excuse me, not the diagonal, the this diagonal, this diagonal line. The orange line and that red line I just drew, or that green diagonal by the red line, are our 4 points, our 4 lines. Okay, so that's case 1. And I'm going to clear this. So you can see if I go to case 2, it's going to start showing this. But if I leave these unchecked, everything is still there. So I can just uncheck these. Case 1 is hidden. It's available if we need it. And there we go, up to case 2. All right, so case 2, notice that we have 3 lines on P, and the points that are not P are collinear. So I maybe need to write that a little better over here. So this should be 3 lines on P with collinearity, right? So that the points, that the 3 points are collinear. All right, but let's take a look at the proof. So notice what we're doing here. We're just going to, we're just naming these things, right? So we're naming M and J and N are the 3 lines that we have that go from P out to the 3 points, okay? And we're going to construct J, right, if they're collinear. That's the point, that A, B, C are collinear. So if A, B, C and collinear, then let's call the line they're on J. So I'm sorry, it was M, K, and N, right? M, N, and K, that were the points from P through the points A, B, and C. And then J is this line that we're drawing here. J is this one, okay? And then since P isn't in the line J, then we have this axiom 5. What does axiom 5 say? Well, axiom 5 says through a line and a point not on that line, there exists a unique line parallel to J, right? That goes through P. So, and that's the orange one, right? The orange one is parallel to J, and it goes through P. So we know that's there because of axiom 5, and that's our 4th line, right? We had 3 lines already when we started, so let's go back with that, right? So, right, we have the 3 lines, and right, we have 1, 2, and 3 lines through P just to get to these points A, B, and C. But since A, B, and C are collinear, this line is parallel to P, and then we're allowed to use the axiom 5 to get the parallel line. That's our 4th line. Cool. So one more case. Case 3. So this is where, again, we have 3 lines through the points, right? So I've got, oops, let me undo. Okay. And so we have 1, 2, and 3 lines already. So all we have to prove is that there's a 4th one somewhere, okay? And here we're just doing the same thing. We're naming everything. But notice this bit, we're going to construct lines connecting all the points. So remember, the points that we're connecting I just put little red dots in them. So we're going to construct AB, BC, and AC. So those are the lines that we threw in new, right? So you can see that. These are the 3 lines we're adding. All right, and I put a dotted line to illustrate that we don't know. Remember, we're not proving based on this model. We don't know that there's an intersection point there. We're just saying whatever those lines are, connect them. Connect them back to P. To connect them to each other. Connect A to B, connect B to C, and connect A to C. But what we do know is that each of them will have a third point, right? So there's a third point on all of them, and I've made them blue. So I'm putting the red dot in the middle of the blue so you can see that. All right. Well, so what we're saying is we're going to join P to each of those points. Now, the problem is that you might have some that are already on lines that go through P, like this one. Okay. But by axiom 4 and axiom 2, they can't all be that way. Let me show you the last point, and then we'll go back and see why something else. So, well, there's actually a point in this. There's a line in here that works, right? And it actually goes through too, right? There's this line in the geometry, but that is our 4th line, right? So we're good. But we just have at most one of these that can go through K, and that's a combinatorics argument. Let me see if I can make that clear. Okay, so for example, this point here, it can't be on one of the lines we've already drawn. We know that these 4 points are on different lines, right? So what if I had a line that did like this? Well, that breaks axiom 4, which says that there is one line, a unique line on any 2 points. Well, so we're talking about these 2 points, right? There's this line that's on them, and now we have the other red line on them. So we know that none of the lines that we've drawn already can include this point. Same thing, right? We couldn't have something like this happening because we would then end up with 2 lines joining P and this point here. So, and the same thing is true for this one over here. So yes, we can have one of these lines, one of these points be on one of these lines, but we're always going to have one extra for which that we can draw another line. So that'll be our 4th line in the geometry, and then we're done. Okay, so I'm done with the proof. Like to do a couple of things. Oops. First hit Control Z to not mess that up. So the technology that I'm using, right? So I wanted things to appear and then appear early and then disappear late. So this is just on and off, right? I don't really have a choice to turn it on and then, or to turn it off and then on and then back off. Okay, so this is really cool. I love them. But if you're going to use something like this, where you want something to turn on and turn off and back on, then you need to use a slider. So let me show you this. This case, for example, actually in these checkboxes, if you go to settings, you'll see when you go to advanced, they have this 0 less than n less than 2. Well, basically when n is equal to 1, that is going to evaluate as true. And that's where you're seeing this happen, right? So when I'm at 0, none of this shows up. Over here, it's blank, right? And when it is equal to 2 or 3, it goes away. But when it's equal to 1, I have these things showing up and can use them. And so that's the way you can use a slider. Now, I made mine integers from 0 to 3, and that's fine. You can use other kinds of sliders, but that will allow you to use inequalities. And by the way, you can use compound inequalities like 0 less than n less than 1 and n equals 3. Now, that's pretty complicated. I'm not going over that in this video, but just showing you the technology that I'm using Also, I will say that to get different lines to turn on at different times, I had to name several extra lines. So I'll just show you down here at the bottom that there are some additional points. X, that's the point 1 comma 1. Why? Well, I need it to show up later in one of my cases proofs, but it's already being used early on, so I don't have control of it. So there's another point that appears later and jumps in there. The same thing with 2 comma 1 is controlled. So that's this one here, right? So that's another way if you need a point that's already controlled by something you created earlier, you can just make another point to jump in on top and hide and show that point as well. So there you go. There's the proof. Let's jump over here to proof 3, and I just want to think about this, and that's why we have this that I created. So we can take a look at our proof and then see by trying some different configurations where we aren't just using 1, 2, and 3. So let's go over the situation. Right, we're going to have 3 non-collinear points. So we're going to be in case 3. And what we're trying to do is we're trying to create the lines AB, BC, and AC. All right, so let's take a look over here. And I've got one situation drawn, right, with 3 non-collinear points, so A, B, and C. And again, remember that there's a lot of different configurations that can happen here. All right, so let's take a look. Let's join. So what the proof says is that we create these line segments that join A, B, and C, and the argument is that there'll be something there to join with P to make the 4th line. All right. So let's do this. It's one of these, right? Now this is interesting. Look, I just joined all 3 lines, right? So or what I'm saying is, right, that this part where they're connected, well, that's actually this arc has connected them, right? And these are connected, these are connected. Oh, but you know what? This is case 2. Okay, so when I have this situation, I haven't actually created case 3. I actually have collinear points. And what's the proof there? Well, the proof there is that there's a unique parallel that goes through P that'll be the 4th line, right? There's some other parallel line in there. And there you go, right? There's a parallel line through P that is not on that red curved line. So this is actually case 2. Let's back up. So now let's try it. Let's see if this works. We have 3 lines, and to my knowledge, there's not a line that connects these 3, so we should be good. Okay, let's see what lines we need. So to join, right, so we've joined the 2 points there on the right, and now we've joined those 2 with the diagonal. And then what do we need? We need something that goes from here around to here, which I believe is 11 down here. Right. Okay. So now we've joined the points. And I just want to make it clear that some of the points we've added aren't really available to us, right? For example, this is a point that we've added. Oh, I'm sorry, it was already there. Let's see. So this is the point that we're going to use, right? This point right here joins, A and C, right? And it can be joined also, right? The 3rd point on this line, right, that joins these 2 is available. And we even have this one up here, but we're going to use this line, right? This will be the 4th line according to this proof, right? So that's just showing you some different configurations, and why those cases, those case 2 and case 3, work the way they do. All right, so I hope this was instructional, both in terms of how to use the checkboxes to turn things on and off and show different pieces of the puzzle, and also in terms of explaining why it is that in Young's geometry every point is on at least 4 lines. I'll be back in a bit with a proof that a point in Young's geometry cannot be on 5 or more lines.